We'll be looking at question 21, June 2024 paper. In this question, it's about redox reactions and electrode potentials. Now, it shows you a flow chart of barium, which is a group 2 element, and its different compounds. It's asking write balanced equations for reaction 1 and reaction 2. As you can see in reaction 1, you are getting barium and converting it into an oxide. So very simply, all we're doing here is reacting barium with oxygen to give you its oxide. And the formula is BaO, which you all should know because barium is in group 2, which forms a plus or 2+ ion, and oxygen forms a 2- ion. So we just need one of each. With reaction 2, you've got a barium oxide turning into a hydroxide. Let's have a look here. So you've got BaO, and it's being converted into a hydroxide, BaOH2. Can you see that you're getting more hydrogen and more oxygen in the compound? And what contains hydrogen and oxygen is water. Reaction 3, what type of reaction is it when you're getting a hydroxide? You're reacting it with something to give you a chloride, which is a salt. And as a salt, we know an acid plus an alkali goes on to give you a salt and water. So this type of a reaction is an acid base or a neutralization reaction. What is a neutralization? Where you've got a H plus reacting with a base. Moving on. This question is about potassium iodate tablets. Prevent the uptake of radioactive iodine in the human body following a nuclear accident. The mass of potassium iodate, KiO3, in a tablet can be determined by a reaction with aqueous solution of potassium iodide. You see in this reaction, under acidic conditions, when you add iodide ions to iodate, what happens, it actually gives off iodine, and we can determine the amount of iodate that was originally there based on some calculations. So let's have a look at what they've given us. A chemist finds that 2 tablets, not 1 but 2, react exactly with this much potassium iodide. 26.2, which is your volume, and you've got your concentration. It's asking calculate the mass in milligrams of KiO3 in 1 tablet. Now, so 39.1, and let me just get my periodic table, which we've been using some values. I'll just get this ready, which I can refer to quickly afterwards. Right, let's do this. Whenever we're given volume concentration, the first thing we can do is work out the mass. So 26.2 multiplied by, let's convert it to decimeters cubed first, by the concentration gives you 3.93 times 10 to the minus 3 moles. What we've worked out here is the concentration, or sorry, the moles of iodate. Notice the ratio between the iodide ions and the iodate KiO3 minus ions is a 1:5 ratio. Let's write down the 1:5 ratio. How do you make 5 into 1? You divide it by 5. So we do 3.93 times 10 to the minus 3. We're going to divide that by 5. This gives us the moles of iodate. Let's divide that by 5. 7.86 times 10 to the minus 4. What we're then going to do is we need to, this is the moles. We need to convert this into mass. We have learnt that the relative formula mass, which is in grams per mole, multiplied by the amount which is in amount is in moles, is equal to the mass, which is in grams. You can see from here that per mole and the mole will cancel out to give you grams. So what is the relative formula mass of KiO3? 3/16 give you a 48. Iodine is 126.9. And potassium is 39.1. Whoops. This goes on to give you 214. So let's get that. 7.86 times 10 to the minus 4 multiplied by 214. This gives you the mass of KiO3 in 2 tablets. Now, and the answer is also in grams. So what we're going to do, how do you convert grams into milligrams? We times it by 1,000. And we then divide it by 2 because we want to know the mass of KiO3 in 1 tablet. I'll just make a little note here. This is grams to milligrams, and this is to work out the mass in each tablet. So 7.86 times 10 to the minus 4 times 214 times 1,000 to convert the grams into milligrams, and divide by 2 because we want to know the mass in 1 tablet. They want the answer to the nearest whole number. Calculator says 84.102. 84 is to the nearest whole number. And you get 4 out of 4 marks for that. Next question is to do with standard electrode potentials. It's saying they are measured by comparison with a reference half cell. What is that reference half cell? That reference half cell is known as the standard hydrogen electrode, SHE, standard hydrogen electrode. We compare all other half cells to this. Now, it's asking, draw a labeled diagram and show how the standard electrode potential could be measured for the redox system below. What is the redox system below? It's iron 3+ and iron 2+. So here, what would we do? We're going to have a solution. The first solution is going to be on the left-hand side. We're going to have, let's choose a color. We're going to have hydrogen gas being bubbled into it. We've got hydrogen gas, and the solution itself is going to be a strong acid. What kind of strong acid could we use? We could use HCl. And what are the standard conditions of the concentration it's going to be, that comes on to the next question. We cannot answer it there actually. Actually, I'll just do it here. 1.0 times 1.0 moles per decimeter cubed. That's your standard concentration. Now, the pressure of the gas is going to be at 101 kilopascal pressure of the hydrogen gas. And what temperature is this going to take place at? The standard temperature of 298 Kelvin. Remember, this has to be labeled. So what is this electrode here? This electrode, because we need an inert, unreactive electrode that is able to sort of carry the current, we use platinum, PT. We've got our voltmeter here, voltmeter, high resistance voltmeter that records the voltage. We've got what connects both half cells is your salt bridge. And the other half cell is going to be of the redox system that's given in the question. And what we do here, we're going to have Fe2 plus solution, could be iron 2 chloride, for example, and Fe3 plus solution. This could be iron 3 chloride. They're both going to be at 1.0 moles per decimeter cubed, being the standard concentration. It will be again at 298 Kelvin standard temperature. And the electrode, we need something inert that doesn't chemically react. We use platinum again. And this gets you all 4 marks for this diagram. This question, you're provided with the electrode potential values. So there's quite a bit going on here. It says many electric vehicles are powered by lithium-ion cells. Hydrogen-oxygen fuel cells can be also used to power vehicles. You've got your 6 redox systems shown below, and it's going to ask you questions on them. Let's look at the first question. It says a lithium-ion cell involves redox system 1 and 5. We've got this one and this one. Construct the overall equation for a lithium-ion cell. You know what? This whole topic can be summarized by this one rule. That one rule is when you're combining 2 redox systems, whichever one is the more negative, that one you flip the equation. That goes in reverse. So the one that's more negative, which is this one, oops, more negative, and you flip it, and so this was going to be going in this direction. So what you've got is asking for an overall equation. So what we do Li this, what we got on the other side, Li plus CO, oops, cobalt 4 oxide. You got your electron there. Then we got our arrow to give us Li and Li plus and an electron. To get the overall equation, whatever is on both sides, we cross them out. So there's electron there, Li plus here, and we have our overall equation. Li plus CO04 to give you LiCO02. It's a bit of working out for a 1 mark question. That's how you would do it. Next question. Hydrogen oxygen fuel cells can operate in either acidic or alkaline. Now show that for acidic and alkaline hydrogen oxygen fuel cells, the standard electrode, the standard cell potential, and the overall cell reactions are the same. Now, if you look at for acidic hydrogen oxygen fuel cells, I've highlighted which ones apply to the acidic. If you look at these two highlighted blue, you'll notice that you got hydrogen reacting with oxygen under acidic conditions. That's why we're going to use redox systems 3 and 4. Remember, whichever is the more negative one out of the two redox systems, we flip that, we make that equation go in reverse. So what we've got, this is more negative. So this will go in this direction. So it was asking for, what was else? The standard cell potentials and the overall cell equations are the same. So look at this. You've got H2, which goes on to give you 2H plus and 2 electrons. The other equation is O2 plus 4H plus 4 electrons. That gives you 2H2O. Notice the electrons are not balanced. So what we can do in that case is double the first equation. And when we, the overall equation, that cancels out with this, these electrons with these. So what you'd get is 2H2 plus O2 goes on to give you 2H2O. Now, if you look at the electrode potential of the cell, this is the formula. The numerical value is always the positive minus the negative. So if you look at the acidic highlighted blue, it's going to be plus so plus 1.23 minus 0 will still give you plus 1.23 volts. Okay. For the alkaline one, highlighted pink, which one is the more negative out of the two? It's the redox system 2. So we write more negative. And being more negative, we're going to flip that. Remember, this is under alkaline conditions. How do we know it's alkaline? Because of the hydroxide ions. And so what we do, let's just zoom out a bit there. You've got, so whichever is the more negative, we flip that. So we're going to have H2 plus 2OH minus, which goes on to give you 2H2O and 2 electrons. The other redox system 4 is O2, in the presence of some water, and you've got your electrons to give you 4OH minus ions. Again, we need to balance the electrons. To balance the electrons, you've got 4 here and 2 there. So the first equation, we need to double it. So we put a big 2 there. Let's make this into a 4, make this into a 4, make this into a 4. And you'll notice again, Whatever is on both sides, we can cancel out. You've got 4 electrons here, 4 electrons here. We've got 4 OHs here and 4 OHs here. There was originally a 2 there that I missed out. So we're going to cancel 2 waters with just 2 of these. And so what the overall equation will be is 2H2 plus O2 goes on to give you not 4 waters, but 2, because 2 cancelled out from here. 2H2O. Ladies and gentlemen, you'll notice that this overall equation and this overall equation is the same, irrespective if it's under acidic conditions or alkaline conditions. Let's do the electrode potential value. Let's calculate that. The electrode potential of the cell is going to be, remember, the more positive minus the more negative. And that will give you, so you got plus 0.40 minus 0.83. And that gives you plus 1.23. Again, ladies and gentlemen, you'll notice that the electrode potential of the cell, of a hydrogen-oxygen fuel cell, will be the same, irrespective if it's under acidic or alkaline conditions. And with that, you'll get all 3 marks. That brings us to the end of this question. I will see you shortly.